Hello, my name is Vihaan Misra, and today I'm presenting my work on sketch-to-image synthesis with semantic priors conducted as a part of the Robotics Institute Summer Scholars Program of Carnegie Mellon University. So this project is about converting text and sketch inputs to a natural and realistic looking image. So the first question that might come to your mind is why sketches? Why do we need sketches and why can't we just use text prompts for the same task? So I'm going to show you some quotes which will highlight the importance of sketches, and not just sketches but paintings and visual depictions in our day-to-day life. A poet would be overcome by sleep and hunger before being able to describe with words what a painter is able to depict in an instant. This is the crux of the project. This is the crux of the motivation. Our motivation is not to bombard users and rely on the user to know a lot about a language and keep editing their text prompts or rephrase their text entirely to get something that they want. One of the most famous phrases that you might have heard is a picture is worth 1,000 words. So you can't expect the user to write 1,000 words about or when they can do the same with just a sketch. So I'll start with an example. So let's say we take this basic prompt. A cat sitting down looking left with the left ear bigger than the other and the tail is coming out towards the right. So notice how I have used various directions and various direction senses that can cause some confusion for a model but is very easy to understand for you. So this is some outputs of the state-of-the-art text-to-image generator, DALL-E. You can observe in these images that only one of them is looking actually towards the left, and the model has completely ignored the one ear being bigger than the other part. And as also the tail is not showing up in at least two of these pictures, and not in the right direction in the other two. And if you want to convey the same information using a sketch, see how easy it is. You can draw this in around 30-45 seconds, maybe more depending on your artistic skill, but you can see how easy it is to convey the same idea using just a sketch. So I would like to talk about the related work in this domain that has already been done. So the most famous works have been the DALL-E and the ImageGen. DALL-E was created by OpenAI and ImageGen was created by Google. So they follow a basic uh, method or framework that we call transformers, and basically particularly vision transformers. So what they do is basically take in a text input from the user, and they use that text input to generate an embedding. These embeddings are feed it to a transformer, and this transformer is responsible for generating images. Now, these two are different in the sense of how they generate those embeddings and how they process those embeddings, but both of these only take a text input as the input, and it has several advantages. One is that it can generate an image of particularly any category that you want, uh, any field that you want, any scene that you want. It will probably give you some kind of output. And moreover, because they're trained on really large data sets and on billions of parameters, the quality of generated images is very high. And relevancy is something you can, that depends on the prompt and something that is debatable. But yeah, it generates quite good and relevant images. But the disadvantage of it is the same as I stated earlier, that it only is constrained by text. It only takes in a text input. And when you take only a text input, you restrict the user to convey their idea freely. And the other major advantage is very hard to train, because these images require a large amount of data, and the amount of images that they use are quite large, so it's very hard to train these models, and not open source. Yeah. And the one more interesting work that I would like to talk about is make a scene. Now this uses the same basic framework of using an autoregressive scene-based transformer, but what they do extra is use a semantic input. So along with the text input, they use a semantic map that can be input to the transformer as a optional input, which increases the quality and the relevancy of the output image by a lot. Moreover, they give a lot more quality and emphasis on the scenes. So, like if you have a face in the scene, it will give a lot of emphasis on the eyebrows or the eyes. So, whatever quality you want the eyebrows or eyes to be in, it will change that accordingly. The modifications in losses in the form of emphasis and perceptual knowledge is feature matching over task specific pre-trained networks. So this is the like the eyebrow and eye thing that I talked about. So it's basically for specific region awareness of the image, of knowing which object is where based on their semantic tokens. And still, it's missing two key things. One is trainability, because it again is trained on a really large data set, and it's hard to get those kind of computational resources and storage and databases to actually train your model. And again, it's not you can't expect every user to be able to edit semantic maps as well as change the text input. So it's these are the two key disadvantages. So one work that I found really interesting was Sketch Your Own GAN. And as you can see from the video, it uses a pre-trained model and then a sketch input from the user. This sketch input is then fed to the pre-trained cat model, and that sketch is used to generate images that of cat that matches the particular input sketch. Now this is particularly interesting because it helps the user to generate infinite amount of images from just a couple of sketches, and it creates a custom GAN model for given sketch input. It basically works on two kinds of losses, an image loss and a sketch loss. So the image loss helps to maintain the quality, and the sketch loss helps to maintain the pose to match to that of what the user wants. But it's still missing a key thing, is that it doesn't take any text input, and that is a downside for the user, because the user will now not have a semantic input of what they actually want. And one other key loss of this method is that it's only you can only generate images if you have the pre-trained GAN model on that cat. So say if you want to generate images of dog using sketches, so you will need a GAN model that has been pre-trained on a dog dataset or a horse dataset or whichever dataset that you want. You will have to need a GAN model that has been pre-trained on that. So now I'll present our method, what we devised. So basically, we use three main components. One is the StyleGAN XL. The StyleGAN XL is a really large GAN model that has been trained on the entire ImageNet dataset. So it has over 1,000 classes in it. And the second component that we include is the clip loss. Now, clip loss is for generating embeddings based on visual inputs and visual and semantic inputs, and it helps to improve the relevance of output image. And the third loss that we use is the same as the Sketch Your Own GAN paper, which is the image loss, which helps maintain the quality of the generated images. This is an overview of how the model looks. You can see the P model is the photo sketch model, which is used to generate sketches or contours of input images. This helps us to match the contour of an generated image to what the user wants, and gives us a sketch loss term which is used to match the user sketch. And the second thing that we use is the clip model, which takes in the input prompt as the input and generates a text loss. And the third loss that we use is the image loss, which takes in the generated image and a real image sampled from the training dataset of the generator to generate an image loss. These three losses together help form our optimizing equation, and guide the training of the generative model. So I'll show you some current results which we have as of now. Uh, as you can see, they are not actually very good, but you can see the model has started to learn in the correct direction, as the sketch of the generated image is matching quite close to what the user wants. So we are in the process of tuning the parameters and tuning the weights of the losses to improve the outputs, but currently the model is in the right direction. Finally, I would like to thank Peter Schalderbrand and Professor Gino for supervising this summer study and their crucial mentorship and direction for the same. We are grateful to Professor John Dolan and Rachel Birkin for organizing this. I would like to express my gratitude to CMU Robotics Institute for supporting the study. Thank you.